Okay, so now we're ready to work on the second problem in that particular homework set. I have it on screen here. It's 21216 ODW. We have air coming in at a relatively high temperature and a very relatively low relative humidity. So this is hot, dry air coming in, and it enters an evaporative cooler with a given flow rate. This is an English problem. We have the air then leaves at 70 degrees, and we want to determine then, if that is the case, how much mass flow of water had to come in as liquid in order to evaporate and to cause the hot, dry air to cool down. And so one of the things we're going to assume is that the wet bulb temperatures remain constant along the flow. And so basically this is an adiabatic saturation type of problem where the wet bulb temperature remains constant. So on the psychometric chart, we're following one of those wet bulb lines up that are basically correspond to a adiabatic type of process. And so with that in mind, we'll go to our test app. Once again, it is a flowing system, an HVAC psychometric flowing system. And in this particular case, we're going to again assign a state 1 as the incoming hot, dry air. It's coming in. We're going to select the English version. We're going to say that it's at 1 atmosphere. And so we see that it defaults to 1 atmosphere. And what we have coming in is at a temperature in Fahrenheit of 110 degrees Fahrenheit. And along with that 110 degrees Fahrenheit, we are told that it's 10% relative humidity. And so if we put it into percentage, 10% relative humidity. So with this temperature and this relative humidity, it calculates the value of the omega, the humidity ratio, and everything else is determined for the state itself. We also know that it's coming in at 5,500 cubic feet per minute. And so that is the volume flow rate. And we see that the software only has cubic feet per second. And so because of that, we have to make sure that when we put in the 5,500, we have to divide that by 60 in order to have it come in at that many. If that's the per minute rate, we divide it by 60 to get the per second rate. And so in essence then, this is our volume flow rate that consists of 223 pounds per second. And with that, we have water vapor coming in at 1.21. And again, we see that if we take this 1.2 and divide it by this, we get an omega humidity ratio of about 0.005. If we look at our graphics panel, in this particular case, we see that we have, again, a very low humidity ratio at the temperature in question. Okay, so we've gotten our first state, and then at this first state, we see that the wet bulb temperature is 68.1 degrees Fahrenheit. And so that's what's going to stay constant as we go to state 2. And so we can go ahead and we can put in our our value at state 2, which is the wet bulb temperature 1. Again, we have 1 atmosphere pressure here, so we can put in that the pressure is equal to P1 at this particular point. So we have the wet bulb temperature, and in this particular case, we are adding, we are going to be adding liquid water. What do we know is the same? We also know that the m dot of the dry air is equal to the m dot coming in. And so we have that. Again, our flow rate of water will be determined from our device panel as we go through and perform an energy and a mass conservation on both the water and the air. And so we have everything that we know at this particular point. We're going to then set up a state 3, and our state 3 is going to be our liquid water. And so our liquid water, we're going to assume that the water comes in at a certain temperature. And so we'll go ahead and assume that the water comes in at the temperature associated with the cool, moist air. And so since our output is at 70 degrees, we're going to say that the water is liquid water. So a quality of 0 and a temperature of 70 degrees. If we go back to state 2, we see that state 2, it was actually stated in the problem that the moist air leaves at 70 degrees. And so that is the second thermodynamic property in addition to the wet bulb temperature and the known pressure with this flow rate of air, so that state 2 is actually determined. So not only do we have here the relative humidity coming in, and we have the mass, we need to determine the mass flow rate of the water. We have the relative humidity exiting, and so we'll put that in percentage. It's 90.96. Okay, that's basically due to that condition being specified and how much water is associated with that. We now are ready to, once we specify our state 3 as our liquid water, we'll be able to determine the mass flow rate of the water from the device panel that we set up. And so on the device panel, we have come in at state 1, which is moist air mixture. We leave at state 2, which is the moist air mixture, but we also are bringing in the liquid water at this particular point. So it will calculate then for this humidification process, because of the fact that it's an evaporative cooler, it's going to calculate then what this flow rate of water has to be, because we've defined how much water is actually in the final state based on the fact that we know that the wet bulb stayed the same and the temperature went down to 70. So no heat transfer and no heat transfer and no work in this particular process. And what will happen then when we do a super calculate, it now has enough information from the device panel to calculate for state 3 how much water was actually brought in during that process. And so if I bring that to pounds per second, we see it is 1.98 pounds per second of water that was added to the system. So what we have observed here in this particular problem is we came in with a certain amount of water, 1.218 pounds per second. We ended up with 3.202 pounds per second, and the difference then is what has been calculated from the mass conservation in the device panel. The mass conservation along with the energy conservation was what allowed us to solve this particular problem. Again, if we were to go to the graphics panel, we see that these are our two state points. This was our incoming. This was our lower temperature, higher humidity. And so we allowed ourselves to have a higher humidity by allowing the liquid water to go in and evaporating. The energy for the evaporation when it came from the warm air, and so we basically brought the 110 degree air down to 70 degrees. 40 degrees of cooling by allowing the water, the liquid water, to evaporate, join the moist air to have a much more humid relative humidity close to saturation, but the temperature was quite low. And so this is a technique that is used in a lot of hot, dry climates to actually air condition with the inclusion of humidity into the room. If one was in a moist, hot climate, one cannot really add any additional moisture to affect the cooling process. And so this then is the end of our second problem.